Today in my video tutorial, I am going to explain how to calculate the pH of a buffer solution. Now, calculating the pH of a buffer solution can be tricky sometimes because we have this equation, the Henderson Hasselbalch equation. Sometimes we use it, but sometimes we cannot use it. So let's discuss when it is okay to use this equation and calculate the pH of a buffer. So, in this example given here, the first one, what's the pH of a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate? The given Ka is 1.4 times 10 to the power negative 4. Now, in this question, we can use the Henderson-Hasselbalch equation. Why? Because the given concentrations of the buffer, the given concentrations 0.12 molar and 0.10 molar are large enough when we compare them to the given Ka, are large enough compared to the given Ka of the buffer. So this Ka is 1.4 times 10 to the power negative 4, which is relatively small if I compare it to the concentrations. And this is the only case when we can use the Henderson-Hasselbalch equation. So therefore, pH equal pKa plus log of the base, which is C3H5O3 minus. It's this part because Na plus is a pH neutral, so it's not a base, over the acid, which is in this case HC3H5O3. Now we have the Ka. pKa is minus log the given Ka, 1.4 times 10 to the power negative 4, plus log the concentrations, which is 0.12, we substitute over 0.10. So the final answer is 3.85 and log 0.12 over 0.10 is negative 0.08, and the final answer is 3.77. This is the pH of an acidic buffer. Now, case 2, when we cannot use the Henderson-Hasselbalch equation. And this is an example given. A buffer, they need to calculate the buffer of a solution containing 1.0 times 10 to the power negative 3 molar and 1.0 times 10 to the power negative 4 molar of the base. So first, let me show you if I use the Henderson-Hasselbalch equation, what will be the calculated pH. So pH equal pKa, which is going to be minus log of this value, minus log 1.8 times 10 to the power negative 5, plus log, I'm going to write it here just in case you got confused so that you don't forget the Henderson equation. So log of the base, which is 1.0 times 10 to the power negative 4 over 1.0 times 10 to the power negative 3. That's the concentration of the acid. So doing our calculations, we get a pH of 3.74, and that is a wrong value. It's not real. Why? Let me prove it to you by doing the ICE table. This is the right way. The concentrations given here are very close to the given Ka. So using the Henderson is not really correct. So let's do the traditional way, which we start by writing an ionization equation. This is the equation of showing the buffer. CH3, COO minus, and H3O plus. So here, initially, you have 1.0 times 10 to the power negative 3. And also you have in this mixture, since this is a buffer, you have the conjugate base. So the change would be a consumption from here, and we obtain more and more of these substances. And when we reach equilibrium, the remaining concentration of CH3COO minus COOH would be 1.0 times 10 to the power negative 3 minus X, and 1.0 times 10 to the power negative 4 plus X and X. So here's the ICE table. Now next, we substitute, we write the formula of Ka, which is the concentration of H3O plus multiplied by CH3COO minus over the concentration of CH3COOH. So we substitute taking the value of Ka. So 1.80 times 10 to the power negative 5 equal H3O plus CH3COO minus over the concentration of CH3COOH. And here we cannot make an assumption, no assumptions, because the value of X is going to be so close to the value of Ka. So we need to distribute this equation and multiply these together. So 1.80 times 10 to the power negative 5 multiplied by 1.0 times 10 to the power negative 3 equal X, 1.0 times 10 to the power negative 4 and X. So if we distribute, we reach a quadratic equation of second degree minus X squared minus 1.18 times 10 to the power negative 4x plus 1.8 times 10 to the power negative 8 equals 0. This is a quadratic equation. So if we plug it into our calculator, we enter the values of A, here it's minus 1, B is negative 1.18 times 10 to the power negative 4, and C is 1.8 times 10 to the power negative 8. Once you enter these values on your calculator will give you two values for X. The first value is negative 2.05 times 10 to the power negative 4, which is impossible, a value to discard because the concentration cannot be a negative value. While the other correct one is 8.75 times 10 to the power negative 5, which is a logic answer. So now when we calculate pH, this is X. I'm going to show you again on the table that X is the concentration of H3O plus, which is going to take me to the pH. So pH is minus log H3O plus, which is minus log of 8.75 times 10 to the power negative 5, and that is not 3.74. The value, the real value of the pH of this buffer is 4.05. So again, recap, the concentrations given in this question were relatively small compared, they are like almost small, just like the Ka. In this case, we cannot use the Henderson Hasselbalch equation. It gave us a wrong value when we used it, but when we did the ICE table over here, the ICE table gave me a correct value for pH. In this question, when the concentrations were large enough and Ka is a small value, using the Henderson Hasselbalch equation was a correct choice.